Hello, welcome to the course SJPHY2C02 Optics, Laser and Electronics. The contents of today's lecture is taken from Electronic Principles by Albert Malvino and Principles of Electronics by V.K. Mehta. In today's class, we will start our discussion on Module 4, Electronics. If you look at the syllabus, it actually starts with the theory of rectifiers. That's a slightly advanced topic, and I personally feel without discussing about the basics of semiconductors and the formation of p-n junction, if we directly get into the theory of rectifiers, that may not make much physical sense to you. So for the sake of completeness, I'm going to start with the fundamental concepts of semiconductor physics. And once we are familiar with the basic concepts, then I will move on to the rectifier circuit. So this is going to take a couple of lectures for me. I understand that some of the basic concepts you have already learned in your +2 classes. But as I said, for the sake of completeness, I need to repeat them. And hopefully, I'm going to discuss them in a more detailed manner compared to what you have studied in your previous classes. Okay. So as you know, electronics is a branch of physics which deals with the study of motion of electrons in materials, in particular semiconducting materials. So materials are classified based on their electrical and electronic properties into conductors, semiconductors, and insulators. Conductors, they have very high conductivity. The inverse of conductivity is known as resistivity. So they have very low resistivity. So if you take a good conductor like copper, its resistivity is very, very low, of the order of 10 to the power minus 8 ohm meters. On the other hand, if you take an insulator like glass, its conductivity is very low. Consequently, resistivity is very high, of the order of 10 to the power 11 ohm meters. For a semiconductor, its conductivity or resistivity is the intermediate of a conductor and an insulator. So their values lies in between that of a conductor and insulator. So if you take a common semiconducting material like germanium, its resistivity is around 0.6 ohm meter. Or if you take another important semiconductor, silicon, it's around 60 ohm meters. Not only the conductivity or resistivity, the band gap also has intermediate values for a semiconductor. And what's band gap? If you take an atom or molecule, you know that the electron there reside in specific energy levels. These are like finite energy levels. But if you take a solid state material like a piece of silicon, it consists of crores and crores of atoms, and since you have a large number of atoms, you do not have finite energy levels there. All the energy levels gets mixed. As a result, you have a continuum of energy levels, which is known as an energy band. So majorly you have two bands, a valence band and a conduction band. So electron can reside either in the valence band, or if you provide some energy, it can go to the conduction band. So these are the allowed regions where the electron can reside in a material. In between these two bands, there is a forbidden region known as the band gap. So you can classify materials based on the extent of the band gap. Now, if you take an insulator, as you can see in this figure, the band gap is very high, typically greater than 5 electron volts. And in the case of a conductor, the band gap is essentially 0, because here the valence band overlaps with the conduction band. And for a semiconductor, you can see the band gap value once again lies in between that of an insulator and a conductor. For example, in the case of silicon, the band gap is 1.1 electron volt, and for germanium it is around 0.7 electron volt. Other important semiconducting materials are selenium, carbon, etc. Okay. One of the important features of a semiconductor material is that the bonds are formed by sharing valence electrons, and these bonds are known as covalent bonds. Now, what do you mean by the sharing of valence electrons? If you take germanium, it has an atomic number of 32. So if you look at the orbital structure, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and finally 4s2, 4p2. So if you look at the shell, the innermost shell has 2 electrons, and the second shell has 2 plus 6, 8 electrons. Then you have 2 plus 6 plus 10, 18 electron, and the outermost orbit, the outermost shell, the valence shell, has 4 electrons, 2 s electrons and 2 p electrons. So it has 4 valence electrons. Same way, if you look at silicon, it has an atomic number of 14. Once again, the valence shell has 4 electrons. Now, what do these electrons do while forming bonds? Since germanium has 4 valence electrons, it can share 1 electron each with 4 neighboring germanium atoms. So, by sharing the electron, they form 4 covalent bonds with 4 neighboring germanium atoms. So, this is how a crystal is formed in the case of germanium. Same way in the case of silicon also, there are 4 valence electrons, so it can form 4 covalent bonds with 4 neighboring silicon atoms. So that's how the crystal gets formed. Now, another important property of the semiconductor is that its resistivity or conductivity is not a constant. It actually varies as a function of temperature. And why this happens? This is because of the intermediate region in which their band gap lies. So as I said, the semiconductor has an average band gap value of around 1 electron volt. Now, if you take absolute zero, the lowest temperature possible, all the electrons are tightly bound to the atom, and the valence electrons are engaged in covalent bonding as shown in this figure. Covalent bonds are very strong, therefore no electrons are freely available. So usually when you look at a band structure like this, all the electrons which take part in covalent bonding, they usually reside in the valence band, and all the free electron means they can freely move around the lattice, they usually reside in the conduction band. So at 0 Kelvin, all the electrons are engaged in covalent bonding, which means all the electrons are in the valence band. There are no electrons in the conduction band. Now typically for a semiconducting material, there are majority of the electrons are in the valence band, and some of the electrons, very few of them, are in the conduction band. This is the usual behavior. Whereas in the case of an insulator, all the electrons are in the valence band, no electron is in the conduction band. That's why they are poor conductors of electricity. And in the case of conductors, there are electrons, plenty of electrons in both valence band and conduction band. That's why they are able to conduct electricity very easily. But when you take a semiconductor and cool it to the absolute zero temperature, what happens? All the electrons are completely engaged in covalent bonding, which means all the electrons are now reside in the valence band. So the band structure of a semiconductor is going to resemble that of an insulator at absolute zero temperatures. In other words, the semiconductor behaves like an insulator when you cool it down. But when you increase temperature, some of the covalent bond breaks and those electrons becomes free. And these electrons, originally they were in the valence band, now they can jump to the conduction band. So now you have some free electrons available. Now when you apply a potential difference to the material, this potential difference acts like a force which pushes the electrons. So as a result, you have a tiny current set up in your material, similar to a conductor. Like you take a battery and take a copper wire, connect one end of the wire to the positive terminal, other end of the wire to the negative terminal. You are essentially applying a potential difference, and this potential difference is going to apply a push onto the electrons, and the electrons set up a current. So that's the behavior of a normal conductor. So when you increase temperature, the semiconductor is also going to behave something like a conducting material. So at 0 Kelvin, there was no current. The semiconductor behaves like an insulator. Its resistance is very, very high. But when you increase temperature, current starts flowing in the material when you apply a potential difference, which means the resistance is decreasing. So in the case of a semiconductor, this is a very, very important observation. When you increase temperature, the resistance of the semiconductor is going to decrease. In other words, the semiconductor has a negative temperature coefficient. You can see from this graph, when you increase temperature, the resistance is going to decrease. On the other hand, if you take a conductor, when you increase temperature, its resistance increases. So this is one fundamental difference between a conductor and a semiconductor. Another important difference between conductor and semiconductor is that in the case of a conductor like copper, the current is mainly due to the flow of free electrons. But in the case of semiconductor, there are two types of current. One is the electron current and second one is the hole current. And what is a hole? So as I said, there are two major bands, the valence band and conduction band, and electrons are electrons which take part in bonding mainly reside in the valence band. But if you supply energy to a material, energy in the form of heat or in the form of light, the bonds break and the electron absorb this energy and move from valence band to conduction band. So originally the electron was in the valence band, now it moved to the conduction band. So what happens to the valence band? There is a vacancy of electron created in the valence band, and this vacancy is known as a hole. As you know, electron is negatively charged, so the absence of electron or the vacancy is positively charged. So the positively charged vacancy is known as a hole. One thing you have to remember, hole is not a true particle like electron. Electron is something which actually exists. You can measure the electron, you can measure its energy, you can measure its momentum, etc. But hole is not a true particle, it is just an absence of electron. It's just like light and darkness. Light is something which exists, right? You can measure it, you can measure its brightness. And what is darkness? Darkness is just the absence of light, right? So you cannot measure darkness as such. So same thing here. So that's why some people call hole as a quasi-particle. Now for every free electron created in a semiconductor, there is a corresponding hole, right? So when you provide thermal energy or light energy, electron jumps from valence band to conduction band. So you have a free electron in the conduction band and a corresponding hole in the valence band, and this is known as electron-hole pair. So that's why you say thermal energy creates electron-hole pairs in a semiconducting material. And just as free electrons in conduction band set up a current when a potential difference is applied, holes in the valence band too set up a current in the opposite direction. This is known as hole current. Let's see how does this happen. So imagine that originally you have an electron at the L position in the valence band. You supply some heat energy. So electron from valence band move to the conduction band. So you have a free electron in the conduction band and a hole at the position L here. Remember, hole is a positively charged vacancy, right? So opposite charges are going to attract. So this positively charged vacancy is going to attract electron from a neighboring site M. So you have a valence electron originally at position M. This electron gets attracted to the hole at L. So it combines with the hole. So what happens? At the place of M, there is a vacancy created, and the vacancy which was initially at L is now compensated by the electron. In other words, the valence electron moves from M to L and the vacancy or the hole moves from L to M. So their directions are just opposite. Now you have a new vacancy at M. What happens? Once again, this positively charged vacancy is going to attract electron from a neighboring site N. So valence electron from N moves to M and the vacancy or the hole from M moves to N. So this keeps repeating. So you have a current due to flow of free electrons in the conduction band in one particular direction and the current due to the flow of holes in the valence band in the opposite direction. That's why I said, unlike conductors, here you have two types of current, the hole current and the electron current. Now semiconductors, you can broadly classify them into two categories. One is the intrinsic semiconductor, meaning if you take a piece of silicon, you have only silicon atoms there, no other foreign atoms. So a semiconductor in its extremely pure form is known as an intrinsic semiconductor. The intrinsic semiconductor is practically useless because this behaves almost like an insulator. Why? Because at room temperature, the number of free electron hole pairs produced in an intrinsic semiconductor is very less. As I said, the current in a semiconductor is set up because of the flow of free electrons and holes. Like you take a semiconductor, apply a potential difference. So the electrons are going to flow towards the positive terminal and the holes are going to flow towards the negative terminal. So you have more number of electron hole pairs, you have better conducting properties in your material. Unfortunately, in the case of intrinsic semiconductors, the number of electron hole pairs is very small, so the current in the intrinsic semiconductor is very weak. This is almost like an insulator. So if you want to use a semiconductor in any practical circuit, you need to improve its conductivity. In other words, you need to improve the number of electrons and holes. And this can be done by adding impurity atoms to a semiconductor crystal. And this process is known as a doping. So when you dope an intrinsic semiconductor, you are basically adding some foreign atom into its lattice, and as a result, its conductivity is going to increase. And such a semiconductor is known as extrinsic semiconductor. So a pure semiconductor is intrinsic semiconductor and a doped semiconductor is extrinsic semiconductor. And the doping concentration is typically very low. Usually for 10 to the power 8 semiconductor atoms, you are going to add one impurity atom. But this is more than enough to alter its electronic properties. And depending on the nature of the dopant, there are two types of extrinsic semiconductors, N-type and P-type. First, let's talk about N-type semiconductor. So as I said, in the case of an intrinsic semiconductor like silicon, it has 4 valence atoms. So each silicon atom is going to form 4 covalent bonds with 4 neighboring silicon atoms. Now in the case of N-type semiconductor, you are going to add a pentavalent impurity atom to the semiconductor crystal. Pentavalent means in the outermost shell it has 5 electrons. Like in the case of arsenic or bismuth or arsenic or antimony or phosphorus, etc. These are pentavalent atoms. Now here what happens? So the 4 valence electrons from the impurity atom form covalent bonds with 4 semiconductor atoms as shown here. So suppose you have a germanium lattice here, you added one impurity atom like arsenic here. So arsenic has 5 valence electron, out of which 4 are going to form covalent bonds, but this 5th electron, this does not take part in bonding, right? So this is a free electron, so it travels to the conduction band and remains free there. So these 4 electrons which take part in bonding, they are in the valence band, they are not free, and they are completely engaged in bonding, but the 5th electron it travels to the conduction band and it remains there as a free electron. Which means when you add an impurity atom, an n-type impurity atom to the semiconductor, you are basically donating an extra electron to the semiconductor. That's why an n-type dopant is known as a donor impurity, something which donates free electron. So each donor atom in the crystal donates one free electron. But there are also a few electron hole pairs generated in the semiconductor due to thermal energy, right? This is the case of an intrinsic semiconductor. Like the moment you supply some heat or light energy, there are electron hole pairs generated. Their number is very, very minimum, and also the number of electrons is same as the number of holes. But when you add an n-type dopant, you are providing extra number of free electrons by virtue of doping. Now if you look at the total number of electrons and holes, the number of free electrons provided by the donor atoms is far greater than the number of holes. So due to the predominance of electrons over holes, they are called as n-type semiconductors. So if you look at the band structure, you have a large number of free electrons in the conduction band and very few number of holes in the valence band. So the conducting properties of an n-type semiconductor arises mainly due to the free electrons. That's why we call free electrons as majority carriers and holes as minority carriers. Now if you look at a p-type semiconductor, the story is just the reverse. So instead of pentavalent impurity atom, we are going to add a trivalent impurity atom like gallium or indium. Trivalent means it has 3 electrons in the valence shell. So here the 3 valence electrons of the impurity atom forms covalent bond with 3 semiconducting atom. But the 4th bond is incomplete, right? For the bond to complete, you need to have a 4th valence electron for the impurity atom. Unfortunately, that is missing here. So the 4th bond is incomplete and there is a shortage of electron in this bond. So the missing electron creates a hole in the valence band. Since hole is positively charged, it can accept a free electron, and then this process is known as recombination. So an impurity atom here behaves like an acceptor. It can accept free electrons. That's why a p-type impurity is known as an acceptor impurity. So as you can see from this figure, each acceptor atom in the crystal produces one hole. And there are also few free electron hole pairs generated in the semiconductor due to thermal energy. Their number is very small, and also the number of free electron is same as number of holes in the case of an intrinsic semiconductor. Now on top of that, you have extra holes provided by the p-type impurity atom. When you look at the total number of electrons and holes, the number of holes provided by the acceptor atoms is far greater than the number of free electrons. Due to the predominance of holes over electrons, these semiconductors are known as p-type semiconductors. So you can see you have a large number of holes in the valence band and very few number of electrons in the conduction band, and the current set up in this material is primarily due to the flow of holes in the valence band. So here holes are the majority carriers and free electrons are the minority carriers. So this is the fundamental difference between n-type and p-type. In n-type you have a large number of free electrons which determines the current, and in the case of p-type you have a larger number of holes which determines the current flow. Now, even though the conductivity of an intrinsic semiconductor is enhanced by adding appropriate dopants, still the conductivity is not very great compared to a good conductor like copper. Right? It has some conductivity, but it still behaves something like a carbon resistor. So it doesn't have much practical utility, but When you take a p-type material and place it next to an n-type material, the junction between two, the border between these two materials, which is known as the p-n junction, this is going to show some remarkable properties, which eventually led to the invention of diodes, transistors, integrated circuits, etc. So let's now try to understand what are the charge dynamics at a p-n junction. So before getting into the details, let's get familiarized with the sign conventions here. So on the p side, I have some circled minus signs. So this is the pentavalent atom, which is the donor atom. Sorry, these are the trivalent atom, which is the acceptor atom. So on top of that, I have a plus sign to indicate the hole associated with this trivalent atom. So you have trivalent atoms in the crystal and each atom providing a hole. Similarly, on the n side, I have a plus sign, circled plus sign. This indicates the pentavalent atom, which are the donor atoms. And on top of each circle, I have a minus sign indicating the free electrons associated with the pentavalent atom. Okay. So as such, p side and n side are electrically neutral. Because if you look here, you have equal number of plus and minus signs here. Here also you have equal number of plus and minus signs. So they are electrically neutral. So when you place a p material next to an n material, the border where p and n regions meet, this is known as a junction diode. Diode is the short form for dielectrodes, two electrodes. Now what happens at the p-n junction? So here you have negatively charged free electrons. Here you have positively charged vacancy. As I said, the opposite charges are going to attract each other. So the electron is going to get attracted towards this vacancy. So the electrons, the free electrons from the n side, diffuse to the p side and combine with the holes there. So as a result, what happens? The hole disappears and the free electron becomes a valence electron. Remember, a free electron is originally residing in the conduction band. When it diffuses to the p side and combines with the hole, because hole resides in the valence band, the electrons comes down from the conduction band to the valence band by releasing some energy, either in the form of heat or light. So in the process of recombination, a conduction electron becomes a valence electron. Now during this diffusion, an electron creates a pair of ions, because when the electron leaves the n side, the pentavalent atom on the n side loses an electron. As a result, it becomes a positive ion. When the electron combines with the hole on the trivalent atom, what happens? The trivalent atom on the p side receives an electron, and in the process it becomes a negative ion. So each electron crossing the junction creates two opposite ions, a positively charged ion on the n side and a negatively charged ion on the p side. So you have a pile of positive ions here, a pile of negative ions here. So essentially you are creating a dipole. So a dipole is created. And in this region, you have no free charges here, because originally you had free electrons in this side and holes on this side. But now when the ions are formed, all the free charges are removed. So this region near the junction devoid of free charges is known as depletion region. So this is a very important step in the evolution of a p-n junction. So initially you have electrons diffusing across the junction, and eventually you have a depletion region forming at the p-n junction. Now once the depletion region forms, what happens? Look at here, you have a pile of negative charges on this side, a pile of positive charges on this side. So this is the depletion region. Now if a free electron wants to diffuse to the other side, what happens? The electron is negatively charged and you have a pile of negative ions on the opposite side. These ions are going to repel the electrons. As a result, the electron is no more able to cross the p-n junction. Same way, if the hole wants to diffuse to the other side, once again you have a pile of positive charges on the opposite side, they are going to repel the holes, so the holes are also not able to diffuse across the junction. So you can say the electric field associated with the dipole is going to inhibit the charge flow or the charge diffusion across the depletion region. Usually people talk in terms of potential rather than the electric field. So you can say the potential developed across the depletion region acts as a barrier against the charge diffusion. So this is known as a potential barrier. So typically the potential barrier is the order of 0.7 volt in the case of silicon and 0.3 volt in the case of germanium. So the barrier potential eventually stops the diffusion of electrons, and if an electron has to cross the p-n junction now, it needs to overcome the potential barrier. So previously the electron was able to freely diffuse across the junction, but once the depletion region is formed, once the potential barrier is set up, you need to provide extra energy to overcome the potential barrier in order to facilitate the charge diffusion. So that's the story of the p-n junction. Now, before closing the discussion on p-n junction, it's imperative that we have some basic idea about the energy levels of a p-n junction. Now, if you look at the valence and conduction bands of p and n, you can see that the energies of p side is slightly higher than the energies of n side, right? So here the conduction band of p is placed slightly above n. Similarly, the valence band of p is also placed slightly above. And why does this happen? This is primarily because of the size of orbits in the pentavalent and trivalent atom. So if you look at the trivalent atom on the p side, it has a +3 core and 3 electrons in the valence shell. Similarly, for a pentavalent atom, it has a +5 core and 5 free electrons or 5 electrons in the valence band. Right? A +5 core attracts electrons more strongly compared to a +3 core. So here the attractive force are stronger. As a result, the valence orbit is going to be closer to the core compared to this case. So here you have only 3 electrons. Here you have only +3 charges attracting the valence orbit. Here you have +5 core attracting the valence orbit. So this orbit is smaller compared to this orbit. So hence the orbits of the trivalent atom on the p side are slightly larger than the orbits of the pentavalent atom on the n side. Since you have larger orbits in the p side, the p bands are slightly higher in energy compared to the n bands. Okay, so this energy difference is primarily due to the difference in size of the valence and conduction band orbits. Now, when you form a junction, what happens to the energy? So you keep a p side next to an n side. We know that there is a small energy difference between them. So before diffusion, this is the energy level difference between p and n. Now, when the electrons starts diffusing across the p-n junction, what happens is the energy difference between p and n side is going to increase. So this is the energy difference before diffusion, and this is the energy difference after diffusion. Why does the energy difference increase in the case of p-n junction formation? Once again, this has something to do with the size of the orbit. What happens during diffusion? So during diffusion, an electron from the n side comes to the p side. It combines with the hole in the trivalent atom. Right? This is what happens. So if you look at the p side, you have a trivalent atom, and it has a vacancy or a hole in its valence band. So imagine you have originally 1, 2, 3, 4, 5, 6, 7. 7 electrons and 1 hole in the valence orbit. Now from the n side, 1 electron comes to the p side and it fills this vacancy. So originally you have 7 electrons and 1 hole. Now you have all the 8 electrons here. Now look at the conduction band orbit here. So initially the 7 electrons are repelling the conduction band orbit, and the positively charged hole is going to attract the conduction band orbit. Okay, so you have 7 repulsion and 1 attraction. But now what happens, you have all the 8 electrons here. All the 8 electrons are going to repel the conduction band orbit. Right? So the repulsion is more here. In other words, after diffusion, the repulsion is more. So as a result, the size of the orbit is going to increase. The valence band orbit is going to push the conduction band orbit further away. So the size of the band is going to increase. Consequently, the p band moves slightly higher in energy compared to the n band after diffusion. Okay. So that's what you can see in this figure. Before diffusion, you have small energy difference. After diffusion, because of the increase in size, the energy difference is going to increase. So this is known as an energy hill. So previously the electron was able to freely diffuse across the junction, but once the energy hill forms, it cannot freely diffuse. So the free electrons on the n side do not have sufficient energy to climb the energy hill. As a result, the diffusion stops. Once the energy hill forms, now if you want to move an electron across the p-n junction, you need to provide extra energy so that it can cross the energy hill. And this process of providing additional energy is known as biasing. So in the next class, we are going to discuss about forward and reverse biasing in a p-n junction diode.